Thanks, Mike. And also thanks to Helen and Chris for asking me to give a talk here. So I'll talk about the crosstalk between global dynamics in the intracluster medium and the circumgalactic medium, and the microphysics at the smallest scales. Although this slide is very pleasant on the eyes, but hopefully it will, by the end of this talk, it will be clear why physics across these scales are quite interesting. So the roadmap of this talk will be, I will first discuss what intracluster medium and circumgalactic medium are, because the audience is not just from cluster community. Although the medium is very messy, I will start off with trying to find some patterns, some length scales, some temperature scales, and then putting some zeroth order picture. And then I will talk about what does the magnetic field do at large scale and small scale. And all these things will be the staging of the talk. And then I will finish with two examples that can be interesting observational probes for AXIS. And then I'll conclude. So to start with, in the large scale picture, of course, the cosmological simulations have been extremely successful in the last decade. And at the very nodes of these, what is known as the cosmic wave, we usually expect to find the largest temperatures or X-ray emission from there. And this is where our intracluster medium typically resides. And so this is a picture of Coma cluster from Chandra Archive. And then in the smaller nodes, typically circumgalactic medium resides. And this is relatively a new topic that people have been excited about, mainly because the temperature is small and it's faint in the X-rays, and there is no easy way to see the CGM. But largely speaking, the general geometry and structure is quite similar. It has a virial radius where material from outside fall in, get shock-heated, and then there in the center there is a supermassive black hole, and there are outflows and inflows. It's generally very messy, and there are mergers, and then substructures move around. So a lot of starring happens in this medium. And many of the so-called circumgalactic medium can be of lower temperatures as well. So in this mess, one thing that we can come up with is because of the gravitational infall or the hierarchical structuring, what it gives us is a so-called self-similarity, and from that we can calculate some temperature scalings, which goes with the virial mass of such gaseous halos. So of course there is starring at the larger scales, and there is starring at the small scales. But overall, we can come up with some temperature of the generally which is characteristic of the medium. So here, just one key takeaway from this plot is nothing but how the temperature profile looks like. This is a cluster-like temperature profile. This is a smaller CGM, and these are very simple models. It doesn't have any radiative process for these profiles for this particular case. And I just want to convey that the main point here is, of course, there are these temperature gradients locally, but largely the temperature is at constant value. And with that idea, for now, if we ignore the details, and if we ignore that this is mainly an ionized medium where the temperature of electron and ion could be different, I'll come to that point later in the talk. We can come up with some basic scaling of how the temperature will be like for a monatomic gas. And that scales with the mass within a node to the power of 2/3. And once we start getting an idea of temperature, we can start to calculate what is called the Coulomb collisional length scales. So this is basically the length scale within which electrons and ions collide and basically start to talk to each other and exchange energy. So at a given characteristic scale, which is the outskirts of this ICM and CGM, if we start to calculate this Coulomb mean free path, and I just chose that there is nothing special. I just chose virial radius to be one region of the outskirts. The main thing to take away is this y-axis, and as you can see that it ranges from 10 kiloparsec to up to 500 kiloparsec. Now, of course, there are some assumptions. In order to plot this, I took isentropic assumption. On the right-hand side, we try to do the same thing for electron gyro radius, and of course, a lot is unknown about the magnetic field. But I just took a very large plasma beta, which is the ratio of the pressure to the magnetic energy, thermal energy to the magnetic energy. And if we just instead use 1000, it will not change a lot. The main thing to look at is this whole range, which is of the order of 10 to the power 12 to 15 orders of magnitude smaller than lambda mean free path. So here I have crossed out weakly. Of course, it's a weakly magnetized medium in terms of plasma beta. But because this length scale is so small, and as we go into the core of ICM or CGM, of course, both these will start decreasing, and at some point it could get very interesting. But generally, there is a huge order of magnitude gap between these length scales. So in this talk particularly, another length scale which is quite interesting is the temperature gradient scales. In the last slide, I actually ignored the small length scales over which temperature can change. But in principle, this can be quite interesting because even for any sort of, for example, if there is a merger, this length scale could be quite large, but for strong shocks, this could be very small. So with these length scales, and just noting that LT could range anywhere in this y-axis, across this y-axis, which means lambda mean free path could be bigger or smaller than LT, we try to first, just immediately it is intuitive that if there is a tangled magnetic field, what happens? If the gyro radius is so small, So if the gyro radius is so small in a tangled magnetic field, it is somewhat easier to sustain temperature contrasts in the perpendicular direction than to the local magnetic field. So that is quite obvious because of the scalings that I just mentioned. But now if we look more into it, magnetic field can do more stuff. So let us first start with a purely ideal MHD scenario. For some reason, let's say so this is the temperature of a Perseus-like cluster, and we are sustaining large-scale temperature contrast. And we want to know what is going on at the interface. So two things can happen. One is that at this interface, lambda mean free path of the electrons, for simplicity, let us now assume just electrons are it's just a single fluid. So lambda mean free path, if it's very small, that means electrons are going to collide very frequently, and there will be an easy exchange of energy at a short time scale. The other scenario that might happen, and this is also pretty common, as I just tried to argue with the values at the virial radius, if the lambda mean free path is much larger, this electron talking is not going to happen very easily. So at that point, what happens is whatever the hottest electron is carrying, like heat-carrying electrons, have some energy. So that will dominate the heat flux. So in other words, there will be a streaming velocity. So the electrons will stream with a certain velocity. Let's say for simplicity, we start off with a hot Maxwellian and a cold Maxwellian. This V stream will just be the thermal velocity of the hot Maxwellian. And what it does is it creates velocity space anisotropy, which in other words, it means that there is a deviation from the Maxwellian for this entire population. And just like any inequilibrium, what it creates is instabilities at the smallest scales. So here comes, this picture is useful to kind of demonstrate it. So this is a 2D 10 electron gyro radius square box. And as you can see, there are magnetic field at various coherent scales. And so it creates a wide range of instabilities. And this is specifically known as fistless. I'll come to that in a bit. So in the first case, where there is frequent collisions between the hot electrons and the cold electrons, there will be easy flow of energy due to these frequent scatterings. For the second case, what happens is this sort of waves start interacting with these electrons. In particular, for this Whistler wave, when the electrons are gyrating at the same frequency as the rotation of the electric field vector, so this is a circularly polarized wave, so the electric field vector also rotates. For those cases, those specific kind of resonances, this sort of interaction becomes very frequent, and it almost effectively acts like a scattering. And what happens is, for example, here, the expected rate at which energy should flow across the interface is so fast that this sort of sustenance of this sort of temperature contrast is almost impossible. On the other hand, here, although there is scattering, this free streaming value is further suppressed. Since specifically what happens is, in the first case, the heat flux or the heat carried by the hottest electrons, that is dominated by this sort of scaling in temperature, while in the second case, there is a factor of 1 by beta. Plasma beta is very large for diffuse medium like ICM and CGM. So this is actually quite small. Now, what it all implies is that in the second case, this sort of temperature contrast is maintained much better than in the first case. So in a way, we can actually distinguish, from the observations, we can actually distinguish which region is collisionally dominated and which region is not. Now, from this first part of the talk, there are two important points. One is that electrons, or let's say electron ions, are either collisionally, very frequently colliding, or they are not, and that can create some difference. Mainly, the magnetic field can become dynamically more important. The other thing is, do we or do we not sustain temperature contrasts in the cluster or the CGM environment? Now, so I'll come to the two examples. For the time constraint, I have picked up compressible temperature contrasts here. So in order to understand whether electron ions are electron ion equilibration timescale is short or not, there has been quite a bit of work in some other fields, for example, in supernova or solar wind shocks, because data is available more easily there. And so in this particular plot in the left, in the y-axis, this is electron pre-shock to post-shock to pre-shock temperature ratio, and on the x-axis, it is the shock Mach number, or in other words, how strong the shock is. So in this particular model, the only consideration that has been taken into account is that the electron and the ion, so it's a two-fluid model, and the electron and ion have the same density jump, or there is charge neutrality. Now, for such a model, if we look into the case of the ions, so the usual expectation is that at the site of the shock, the ions will immediately gain energy, because ion collisional timescale is very much shorter than the electron-ion timescale. So ions will get heated, and the electrons will have a lag behind, and electrons will actually receive the energy from the ions after electron-ion collisions. So now the strong shock sites, thus, are very nice sites to test this hypothesis, or whether electron-ion collisions are happening fast enough. So for example, this solid line is at for a very strong shock, which is high Mach number, and this is the case where electrons and ions behave similarly, or there is, in other words, there is instantaneous thermalization. Electrons immediately gain that energy instead of receiving it from the ions. The more likely scenario is this one, where electrons are adiabatically compressed, and then the electrons start interacting with the ions and receive the energy from the ions. In the cluster case, there has been some work. So, for example, this is a Marger shock. As you can see, this is quite far away from the virial radius. This is almost halfway inside. And there are two models that are tested in this work. One is where instantaneous equilibration happens for electrons, the thing I just now explained. And the other one is the collisional equilibration model. And for that, the way this model works is there is adiabatic compression, and then with the assumption that the kinetic energy is conserved across the shock, one can solve this within the length scale of how far the shock moves within this tau electron ion, which is the collisional timescale. Now, the main takeaway from this plot is that collisional equilibration model, or in other words, where the electrons are first adiabatically compressed and then electrons collide with the ions, that model is much more likely in this particular case. However, the main source of error here was the low photon counts in the pre-shock gas, which actually makes this region quite uncertain. So this is where future observations can give us a better idea of which model is more likely. At this point, I also want to kind of make it a point that while ions are expected to kind of immediately get shock hit because the ion-ion collisional timescale is very short compared to this timescale, there could be a possibility if we go back to the lambda mean free path, there is a possibility that even the ion-ion lambda mean free path is actually of the order of 1 kiloparsec or 2 kiloparsec. And that could be larger than the temperature contrast length scale. So for a purely collisionless case, there is a good chance that magnetic fields are important, and there could be coincidence of non-thermal emission, for example. So this is another indirect, this is also sort of, other than the main question, which is the equilibration timescale, this is also good to indirectly probe whether magnetic fields can be constrained from there. So the second example case that I would take here is weak compressible features. So what we are looking at is the Perseus cluster, and this is the pressure map. And the physical picture is the following, that because of the supermassive black hole at the center, there is active galactic nuclei and these Aegean activities generate large bubbles into the medium, and not just that, it dumps a large amount of energy into the medium. It turns out that quantitatively this energy is, or the rate of the energy dumping is actually just sufficient to combat the cooling rate of this whole medium, cooling by free emission. And that kind of keeps the medium sustained at equilibrium. Now, some of the details are actually missing, like whether this energy is dumped right there, or this, there are waves carrying this energy out to the large radius. So for example, in Perseus, these ripples have been looked at, and there is a case for energy being carried out to large radius by these ripples. So two things that come out of if we can see weak compressible features, two things that come out is number one, there is a case for energy being transported by these waves to large radius. But simultaneously, something else is also true, that in the center, which is the core region, which is actually highly collisional in terms of Coulomb collisional timescales, that region is inefficiently conducting heat. So this as a result, this is kind of quite interesting. Like good theorists, we have some predictions without anything. For example, so this is the same sort of simulations without magnetic field. Sometime back, I was just showing the temperature profile of this particular sort of simulation. But in this case, in this particular case, we do not have magnetic field. We do not have thermal conduction. And what we are trying to do here is just look at the fluctuations. We are dumping energy at the center, and we are trying to see when the fluctuations are more like sound waves. So just to point it out, this black line is actually isobaric fluctuations, and this blue line signify the adiabatic fluctuations. One thing that we found out is that the fluctuations for the compressible case is often quite small if the power is not sufficient, and dominantly there is isobaric fluctuation. So it's not easy to understand whether along this line there is some expansion. But we did get some sweet spot where you get fluctuations at large radius. So for example, so these colors imply, basically this is green is 15 to 45 kpc, and the purple is 45 to 75 kpc. So that means there are some fluctuations at these sort of large radii, which is quite interesting because, as I was saying, that this sustenance of this sort of fluctuations in clusters at large radii will imply simultaneously two things. With this, I will actually come to my conclusion. So the first conclusion is that circumgalactic medium is, of course, the new interesting area because it has not been explored, because it's fainter, so it has not been explored as the clusters. And the virial radius, or the outskirts of all these CGM or the ICM, is actually quite interesting in terms of this microscale physics. What I also discussed is that the Coulomb collisional mean free path can be actually it can have a wide range of values. It can be larger or smaller than the temperature gradient scale. And depending on that, the magnetic field will start becoming interesting. The two important things that I pointed out, just using compressible temperature contrasts, strong or weak compressible temperature contrast, is that we can comment on whether the electron-ion equilibration timescale is as expected or not, and also whether we can sustain temperature contrast and kind of indirectly understand whether some of the plasma scale physics that I explained are at play or not. But I have actually, for the sake of time, I have actually not talked about a whole lot of interesting temperature contrasts which are incompressible. And I have worked in thermal instability. So the length scale of thermal instability or incompressible isobaric temperature contrasts are also very, very interesting, and could be very, very good way to also indirectly constrain on the energy transport process, because if the energy transport is efficient, then we will not get very small scale thermal instability and vice versa. So I'll finish on this with this plot, which I really loved in the white paper, because the contours actually reflect that axis is attempting to look at the very outskirts of the gaseous halos. So this is a cosmological simulation, and from that, this is the emissivity and marking the regions which are going to be targeted by axis. And I'll leave at that.
Great. So do we have any questions if people want to raise their hand? So I have a question. So can you talk a little bit more about kind of the types of like exposure times and targets you would look at with axis when you have, you know, your large increase in sensitivity Like what would you do for your observing program?
I'm not really an observer, so what I was kind of interested in was basically the resolution that. So this is thanks to Helen, the resolution that axis can get into. So, for example, I got interested that the shock region will be can be resolved, and uh, the physical length scales and the angular resolution are in the right sort of ballpark for axis. The exposure, so for example, this is one of the this is one number for this sort of the first kind of strong shock that I mentioned about, and this is with Chandra, which is much bigger, but even the axis can do much better with this.
Great. Chris, I see you have your hand up.
Yeah, no, thanks. I just wanted to expand on that interesting question. I think with Axis, well, okay, let me back up. With Chandra, of course, is really the only extra observatory right now that has a spatial resolution to see things at the mean free path scale. I mean, fundamentally, the mean free path scale in Perseus, for example, is of the order of order of an arcsecond. But you don't have the photons with Chandra to do the kind of spectroscopy that Prakriti is talking about. So I think real key thing with Axis is both that resolution and the number of photons you can gather, which will let you look at the detailed temperature structure on those scales. So I mean, as a sort of question, Prakriti, do I remember correctly that things like precursors, electron precursors in front of shocks, they're typically what 40 mean free paths, something like that?
Yes.
Right.
So, for example, when I was talking about this model, so by precursor, you basically mean the electron temperature just
Yeah,
gradually increases, and that can happen over tens of.
tens of mean free paths. Yeah, I vaguely remember there's a square root of the proton to electron mass ratio in there.
Yeah.
So things like 40. So that's the kind of scale where, I mean, Axis will do an amazing job of getting both photons and spatial resolution there. One shameless plug for the fact that we'll hopefully get our first hint of what this looks like from the new 3 megasecond Perseus observation with Chandra from the legacy observation with Chandra that was just recently approved. That will give us a first look at this, although with Chandra, unfortunately, we've lost the soft band response, so we won't quite get everything we want.
Great. Well, thanks everybody for joining, and thanks for some great talk.